Okay. Anyway, so message of this lecture is there are three things. I mean, this is about cosmology, and I think everybody's interested in working in the cosmology. We know that after all these observations and experimental evidence and so on and so forth, that we do know that our universe started in a very hot and dense stage, which is called Big Bang universe. And this is, I would say, 100% confirmed. We have a very new theory which explains a very, very, very early universe, which we call it the inflationary universe model. And it is still sort of to be proved, hopefully in the near future. But there are ample of evidence which tells us that actually we did have this inflationary stage in the early universe. Inflationary means the exponentially expanding universe. Interestingly, it seems that the current universe is undergoing exponential expansion again. And nobody knows why. And this is another very, very interesting mystery of the universe. Everybody, or maybe not everybody, but many people are working on, which is called, by the way, dark energy in the current universe. Finally, of course, one of the, or maybe the most sort of, important target of cosmology is to understand how the universe was born, how we are here, right? How the space-time was born, and so on and so forth. This is a quite philosophical in some sense, but interestingly, we sort of started to have some tools to investigate such cases, and although it has not been anything is not proved or anything, but there are interesting trials and errors, and which we essentially call it quantum cosmology. And if I have time, I will explain what it is. Anyway, let me start with Einstein's general relativity, which was discovered, or I don't know, invented, how I should say. Anyway, by about 110, almost 110 years ago. The important thing is that by that time, until that time, gravity was considered to be one of the standard forces, including like other maybe electromagnetic force and something like this. And it behaves exactly like the electromagnetic force, except that in the case of electromagnetism, you have positive and negative charges, while in gravity, you only have the positive mass. So it was quite different. And another difference is that so-called this equivalence principle, which tells us that if you have, this is a famous experiment, the Gedanken experiment, Einstein, that if you are in the elevator and free falling, then you don't even cannot tell whether you are in a gravitational field or you are in just sort of the flat space where there's no forces acting. And this equivalence principle actually is the very source of why the gravity is so different from other forces, and which sort of led Einstein to discover this new theory, Einstein general relativity, and which tells you actually it's the space-time, or this four-dimensional space, 2, 3 plus 1. One is time dimension, and that is deformed due to the energy or energy momentum tensor of the matter. And so the right-hand side, you have the energy momentum tensor, which is called T mu nu. The left-hand side, the space-time curvature, or the people call it the Einstein tensor. Essentially, it's the second derivative of how the universe is curved. Is given in this form, and something which is important is there's this 8 by g. G is the Newton's constant, and c is the velocity of light. So it's the gravity combined with relativity, and this is why it is called general relativity. Anyway, this is essentially the only important equation I have in this slide. So once you apply this Einstein equation to universe, now since our universe, I don't know, it's so vast and they have the a very long time scale, large dimensions, space dimensions. So you cannot just deal with everything. So usually you assume some kind of a assumption of what sometimes called principle, and what it is it's called the cosmological principle or Copernican principle, which means let's assume our universe is spatially homogeneous and isotropic, meaning if you go to some other place in this universe, the physics there or how things are there is exactly the same as us here. Or if you look around, we see essentially the same sky if in the large scales. Today we have a very distant galaxies, pictures, and so on and so forth. And those are distributed in a very large scale, essentially in the same way. And if you go to some other places, you see also the same thing. And this is a very, very strong assumption, which make this Einstein equation very, very simple. And then at the same time, from some mathematical theorem, we know, apart from some non-trivial topology, which I don't think I have time to discuss, there are only three possibilities. One is called open universe, which means that the space-time curvature there is not space-time. Space curvature is a negatively curved, so that if you draw a triangle, then sum of these three angles would be less than 180 degrees. Another is the standard flat or Euclidean space. In this case, sum of the angles are equal to 180 degrees, which we know very well. In the case of closed universe, then if the space is positively curved, then sum of the angles becomes bigger than 180. So in principle, we can draw a long sort of straight line in this universe, and they make the very precise measurement of the sum of the angles. We could tell whether your space is open, flat, or closed. Fortunately, or maybe unfortunately, I don't know, it depends on how you look at. Our universe seems to be very, very close to flat. So it's very difficult to actually measure this angle. But anyway, this means it's in some sense unfortunate that we don't have this interesting other possibilities. It seems, at least it's observationally not has supported, but from a theoretical point of view, it makes it much easier to analyze what is going on in our universe, because you can, as a first principle, you can assume this a large-scale homogeneous isotropy, but in addition, you can assume the space is flat. Okay. Anyway, so that's basic things. What's going on? Okay, so if then with this assumption, essentially this Einstein equation, which, as I told you, that the left-hand side is the space-time curvature, and the right-hand side is the energy momentum tensor. But in this homogeneous and isotropic universe, or a space-time model, this left-hand side is just simple sum of two terms. One is called h square, and which is called the expansion of the Hubble parameter of the universe, which tells us how the universe is expanding. In some sense, this is the curvature towards time. Now, the space-time curvature is composed of this a component in time direction and component in three-dimensional direction. But because of this assumption of homogeneity and isotropy, three-dimensional term is simplified to just one. Is this one? Oh yeah. So this k over a squared is the term which represents the space curvature, and as I said, we can in a very good accuracy in most cases we can put k equals 0. Although non-vanishing k may have some interesting sort of results or the theories or maybe observational implications. Anyway, so this a there's some. Is there something that's going on? So I hear some noise. Is that okay? All right. So A is called cosmic scale factor, and it's not so easy to how to say understand it in an intuitive way. Essentially, if, for example, if you consider the closed universe, then A would be the size of the universe. The size of the universe, and if it is open or flat, there's no size. This space is infinitely large. So this is just the characteristic. You just take one length, something. Then if you let the universe expand, then this length expands. So this is kind of the picture of, sorry. I thought oops. Oh. I have so many things in one slide. Anyway, so this is the picture how the universe expands. So the size, some character size A expand. In this case, I'm assuming this flat space, but forget about the flat space for the moment. Then you can just ignore this, and then this equation, this Einstein equation applied to this homogeneous and isotropic universe called Freeman equation becomes very simple. That if you give, say, energy density of the matter, then you know how the universe expands. Or in terms of scale factor can be integrated. If one knows this expansion rate, then you just integrate this expansion rate and exponentiate it. And that gives you essentially the size of the universe. And this Friedman equation was sort of discovered soon after Einstein's discovery. It's like, well, not maybe you shouldn't say soon, but at least within a decade. And this is this equation we always discuss, and we think that we have almost proved that it's correct, that our universe is actually expanding. And one of the most important evidence is that so-called Hubble-Lemaitre's law. By the way, these days we have to include the Lemaitre into this Hubble expansion law, which we used to call it, because now the historians, how to say, natural history people discovered or they confirmed that the Lemaitre found this expansion law a couple of years before Hubble. But anyway, that's a small thing anyway. And currently, so the expansion rate is determined, this Hubble expansion rate, as I said, this is the relative sort of expansion of the scale within, say, some given time. And this is the current sort of value, which is about 70 kilometers per second per megaparsec. 1 megaparsec, this is the unit of length quite often used in cosmology or astrophysics, astronomy, which corresponds to 3 million light years. So if this means that if you sort of go about 3 million light years away, the galaxy at that point would be receding at the speed of about 70 kilometers per second. It's very, very fast. If you can have some vehicle or something, some airplane, something which flies with this speed, then we don't have to take so much time to come to this place from Japan. I don't know how many seconds we need, but in a few minutes time. But anyway, so it's very huge, very rapid expansion in the sort of standard sense. It's a very, very fast. Although but this we don't really feel that anything is expanding far away because the scale is so huge. This scale is like this, as I said, 3 million light years. For example, considering the distance to the sun, our sun, it's only 8 minutes, 8 light minutes, you should say. So compared to that, it's a more than 6, 7 digit difference. Anyway, so this is the discovery, and we think that the Einstein was correct, and actually, as opposed to the homogeneous and isotropy assumption, it also seems to be very well sort of established from all these surveys. This is not a sort of up-to-date survey data, but since this is one of the nicest picture, I always use this. This is called the two-dimensional 2DF a galaxy redshift survey. So it surveys the distribution of galaxies. So each point, this black dot, it's really, each black dot is a galaxy. Galaxy is that includes like, billion or even 10 billion stars or something. It's a huge object, but anyway, which looks like a point. And you see some structures like this, but still, if you look at, say, this left side and right side, all those distribution looks quite similar. So this means that everything looks quite homogeneously distributed. Now, the reason, actually, by the way, this is about the size of 1 gigalight years, which is about 300 megaparsec. This is, and we know that the observable size of a universe is about 10 gigalight years. This is because our universe has been sort of expanding for the last about 10 giga years, and which means that before that, actually, we don't really know what happened or what was there, if there was any space-time or, if there's another universe or something. But as far as our universe is concerned, at least what we understand is that our universe started about 10 giga years before, which means that you cannot go back. And if you think that the light travel, it takes finite time for light to travel from some point to the, our point. Then, by the way, yes, this is another important sort of thing I should have seen. And in this relativity, is it, which one? Oops. Okay. So as this unit of the distance tells you, 1 gigalight year means that it takes light to about 1 giga year to arrive, meaning that if you're looking at something far away, you are looking at past. And this is another interesting sort of thing in cosmology. In cosmology, we cannot sort of, it's very difficult to know what happened at your point, in the early universe. But by looking back or looking far away, and under this assumption of homogeneous and isotropy, you can actually understand what universe would look like, and you can sort of extrapolate this. And of course, all these assumptions must be tested every time you do the observation. So far, there aren't. Almost all the observations are consistent with this global homogeneous and isotropy. So anyway, so this tells us, how important it to go look back and to sort of observe something deep in the space. And that would tell us what our universe looked like in the past. By the way, so you see that currently we have this observation of this size almost. It's not exactly close to the entire sort of observable universe, but it's close to maybe, in terms of length scale, maybe say 30% or something. Although since this is, let's say, it's in this case it's just very thin slice of this three-dimensional space. So the total number of all these galaxies measured is not still far from complete. But still, we are sort of starting to see the end or edge of the universe in this way. But in the about 100 years ago, when Lemaitre and Hubble discovered the expansion of the universe, it was this size, this small size. And it's sort of amazing that, they could discover the expansion by looking at this small region. And my suspicion is that their observational data is driven by theory. It's a theory prejudiced data. But since they were correct, it's okay, huh? Yeah. Anyway, now, so if you consider that this expansion this and you go back in time, because the universe must have been very, very small and dense. And this also tells us, usually if it is what is called adiabatic expansion or adiabatic contraction, the temperature also goes up. And so this means that the early universe must have been very high temperature and high density. And this is the model which was originally a sort of proposed by George Gamow in 1940s, that our universe must have been very hot and dense in the early universe, which means actually there are some elementary particles interactions, high energy interactions going on, and which then you can use the knowledge of those, nuclear physics or particle physics to understand the early universe. Or actually, you could do in the vice versa, and that's what we very often do by using the observation data of cosmology. You can actually constrain or maybe even find some new sort of evidence of some new phenomena or particles in particle physics or nuclear physics. Anyway, so this was. By the way, the name Big Bang, it seems that comes from somebody else who didn't like this theory, and this guy just sort of make a fun of this model. But it turned out this was a really nice model name for this theory, this hot Big Bang, hot and dense universe in the early universe. It's called the hot Big Bang theory, and now it is a sort of a standard name. And now, then, how can we prove that our universe was so hot and dense? And this was fortunately discovered already like 50, 60 years ago by this Benjas and Wilson. And that when they are looking at the radio signals from various directions and try to reduce the radio noise, they found that there are some noise which you cannot get rid of, and it seems that it comes from homogeneously isotropically from everywhere, all the directions. Now, so that this happened, it turned out to be a reminiscence of this hot Big Bang universe. The point is that if you consider this early universe history, then in the beginning you have this early universe, a hot soup of photons and elementary particles flying around and colliding each other, and it's kind of plasma stage. But then during that stage, so this is the sort of a thermal history. Then we think that because of this high, dense and hot environment, you start to, and as that universe start to cool down, all these elementary particles start to sort of join each other and form some nuclei. And this is called the Big Bang nuclear synthesis. And then after maybe 1,000 years or so, the universe becomes cool enough and sparse enough so that the electrons and protons no longer sort of interact each other. They start to combine to form some neutral hydrogen. And this is called a neutralization or decoupling of photons from matter or matter from photons, and which means that if the universe becomes neutral, then the photons will no longer interact with matter, and they can start propagating freely. And also this means that there's no sort of pressure to stop a gravitational collapse. And the radiation pressure is gone already, so the matter can collapse to form stars and galaxies and so on and so forth. And this is the brief history of the universe, the early universe. And the early universe, as I said, essentially you have this plasma stage, but at this about this, I don't know exactly whether this number is really correct or not, but it's almost like 300 or 400,000 years after Big Bang. Then the universe become neutral, and the important thing is that because it becomes neutral, as I said, that the photons which are scattered by those charged particles would no longer be scattered, and they come directly to our Earth. And this is what the Benjamin and Wilson observed, and this is called cosmic molecular background. And it is exactly the same thing like looking at the clouds. For example, if you look at some cloudy day, maybe today is also a bit cloudy, and if you see up, then you see the surface of the cloud. And this means that the surface of a cloud, what we call the last scattering surface of a visual photons. Because if you look at, we could see the surface means that the light from that surface directly comes to your eyes. Same thing happens in the radio case, but at this radio frequency, 100 gigahertz, very interesting thing happened. Actually, there are no real obstacles to scatter those radio waves. So the last scattering surface turned out to be this last scattering surface I just told you here. So in the visual frequency, you can also see the surface of cloud. But in the radio frequency, you can see the surface of last scattering with the very, very early universe, the 300,000 years after Big Bang. That's the amazing sort of consequence of this universe cosmology. And we do have all this very good evidence now. Now, another thing which is important, of course, is why then this high frequency, by the way, at that time it's like ultraviolet or even higher frequency. Now those photons, very hot and dense photons, now behaves like microwave. And the reason is so-called cosmological redshift, that all these photons, when they are propagating, the universe expand, and at the same time, the frequency, the wavelengths of photons are stretched. And because of the stretching, the light which was very blue or maybe ultraviolet, or even higher, maybe X-ray, those becomes redder and redder, and right now, we observe them as microwave. And actually, because of this, we know that our universe was really hot and dense in the early universe. And currently, we have this a very nice observational data, which tells us actually these red points the observation data, and this a bit thin, but the green line is the theoretical the curve called the Planck distribution, and which is the pure thermal equilibrium distribution of those photons, and it's amazing that this the observed data points exactly coincide with thermal spectrum, which tells us that in the early universe it was exactly thermal equilibrium. By the way, the error bar is sort of enlarged by 100 times. So this means that if you see, I don't know if there's any sort of experimentally, how to say, recoverable Planck spectrum in our universe, or maybe in experimentally, because so I would think that this is really a ideal example of Planck distribution, which is provided by the nature. It's amazing. Anyway, okay, let me just go to what would have happened before Big Bang. This is about this inflationary universe model, which was sort of proposed around this about already 30, 40, 50 years ago, almost. Anyway, by many of those people, I cannot explain who did what. But anyway, so that's the idea is that in the early universe, before this hot Big Bang universe, there was a time when the universe expanded exponentially, and by what is called vacuum energy. And the interesting thing is that there is some notion of false vacuum, which was turned out to be a very important notion, while in the quantum field theory, but also at the same time in cosmology. The point is that this false vacuum is locally exactly like standard vacuum, means there's nothing, no any matter, nothing, but it does contain some potential energy, which is called vacuum energy. If the energy density remains the same, as I have shown you in some slides ago, our universe is drawn. The Einstein equation told us the universe is curved. And the right-hand side, you have the energy density, and left-hand side, you have the space-time curvature. Now, as I said, it's observationally, the space curvature is negligible, and then, which means that the curvature must reside in time direction, which is the expansion of the universe. The universe must expand. So this means that if you have some vacuum energy, universe expands. But usually, if you have some expansion or something, then the energy density decreases. But in the case of vacuum energy, because it's vacuum by definition should not change by anything. It's there. The vacuum is already there. Means that vacuum energy also is there. Cannot decrease or increase anything. Because if it is decrease or increase, then it's against the notion of vacuum. So this means vacuum energy remains constant, and then this Hubble expansion rate remains constant, which means we have the exponential expansion, as I have just maybe a few slides ago. Oops. Yeah, here it is. So as I shown you that the characteristic size of a universe, the time derivative of the size is equal to Hubble expansion time times scale factor, and which means that this character scale is exponential of the integral of h. If h is constant, this means exponential expansion. Let me go back. So this automatically tells us that for some reason, if we have the stage in the early universe where the vacuum energy dominates the energy density of the universe, our universe would expand exponentially, and which means you can virtually sort of creating huge energy out of nothing. This is something which is a bit counterintuitive, but this is what happens in the early universe. And then you can easily see that if you have a small universe, we don't know how the universe looked like before inflation, but let's assume that it was some small baby universe, then it could just expand. And in the current observation tells us this expansion was at least 10 to 30 times or more. So it's a huge expansion. And because of this, you create a huge, gigantic size universe. Now, and we think that our universe, the observable universe, as I said, it's about 10 gigalight years size of universe, is a small portion of this gigantic universe. And which means that this universe, whatever you have, any fluctuations or whatever you have in the beginning, would be stretched, completely stretched, and becomes very smooth and homogeneous and isotropic. So, and at the same time, this is the equivalence principle. If you go to the small regions, any space-time region should look like flat. Now, instead of going to a small region, you just make it expand to huge exponential light region. Then our universe would look like flat. Yes. So this essentially can explain homogeneity and isotropy and flatness of the universe. But at the same time, this wasn't actually the most important discovery after this inflationary model was proposed, that the quantum vacuum fluctuations are also stretched to megascales. And so those fluctuations in the very macroscopic scale can become huge and then frozen on the large scale, and later becomes the stars and galaxies, and actually something like this. So to summarize, so what the current understanding of the universe is that we had this false vacuum dominated inflationary stage in the very early universe, and then after a certain time, there was some phase transition type thing which sort of changes all this vacuum energy into heat. And then you create huge amount of particles and everything. And this is the birth of a hot Big Bang universe. And we think this happened probably around after say 10 to 34 seconds after the birth of some birth of some universe. As I said, this birth was not well understood yet, but still, that's the time when this Big Bang, hot Big Bang universe was born. Now, since I don't have much time, let me just quickly go through the evidence. So as I said, the prediction is at least the universe after inflation is extremely flat. But you have this micro quantum vacuum fluctuation grow macroscopic scale to form galaxies and so on and so forth. And these fluctuations leave distinguishable imprints on this cosmic Weisberg background. And this agrees perfectly with the observation, agrees perfectly with theory. So, for example, this is the map of, as I said, so you look back in the radio frequency, you see this last scattering surface, which is, as I said, it's a pure Gaussian Planck distribution, with the fluctuations very, very small, tiny. But if you zoom up by 100,000 times, then you start to see some fluctuations. And this amplitude of fluctuations, relative fluctuation, is 10 to minus 5. And these small fluctuations, although it's very, very small, tiny at this time of the year, which is, as I said, not as said, but as this says, that it's like a one-day old universe if we think that our universe is about 100 years old. Then And at this one day of the universe, you have this small, tiny fluctuation, then later grows to same galaxy and stars, and actually us as well. So everything was sourced by this quantum vacuum fluctuation during inflation. And observation actually fits very well. For example, this is the fluctuation spectrum, and red points are the data points, and the green and blue line is the theory, and as you can see, they agree very well. Now, we do have some mystery again, because we think that after this inflation, that all this false vacuum energy is turned into matter, and that we are living in the universe without any vacuum energy. But it seems that these days we start to see a so-called dark energy, but the dark energy essentially is equal to this vacuum energy, and we still have some remaining vacuum energy. We don't know why. It's a very small but finite vacuum energy, which start to make our universe expand exponentially again. So this is a sort of a very interesting sort of mystery of the current universe, and it may be related to those history in the very early universe. If there's any connections or theories, we have no idea. Some people have some ideas, but we don't have any definite sort of a theory yet. But anyway, this is the current status of our universe. If you think of the constituents of the energy density of the universe, about only 4% are the sort of atoms, and those are what we call baryons, which constitute our bodies and everything, our desks and everything. But the remaining is completely unknown. There are about 22-23% so-called dark matter, which is probably the matter, standard matter, but except that they don't interact with us, so they are called dark. Actually, it's probably, maybe it's, from a physical point of view, it should be called transparent, because it's not dark at all, it's just transparent. But anyway, so this is the dark matter, which we don't know, and which seems to constitute lots of the important part of this matter of the universe. The remaining about 3/4 are constituted of this dark energy, which it looks like vacuum energy, and we don't really know where it comes from and why. And this is the current interesting sort of issues of the cosmology. Yes. Anyway, I think since I don't have much time, I really quickly go through. To see this, going back to this inflationist universe, we have this very strong evidence, but still, it's a bit far from proving this stage. And one of the important proof, if this actually happened, is that they produce not only those vacuum fluctuations in those matter field, but they can also produce fluctuation in space-time itself, which is called gravitons, or gravitational tensormers. And these, if they are produced during inflation, then it can propagate until today without a sort of a scattering much with other matters, because by definition, gravitational interaction is very, very weak. So they can actually propagate directly to us. Now, if we can see such a waves, gravitational waves today, then that would be the real proof of inflationary universe. There are many ideas to detect. One of the ideas is to use this CMB as kind of a detector of gravitational waves. It is known that if this gravitational wave on very large scale is propagating through this CMB, then they would produce so-called B-mode pattern, or some polarization which cannot be produced by standard sort of scalar type or density perturbation type fluctuations. And they may be seen, if we are lucky enough, within 10 years or so. And if we see them, then this is a very, very strong evidence for inflation. Now, let me just quickly, within remaining 5-10 minutes, about what we think about universe before inflation. In this, to understand this, first we have to remember that there's a famous theorem proven by Hawking and Penrose. I guess many people know those name of those people. Hawking is very famous for this wheelchair, and Penrose has got Nobel Prize for this proof of the existence of black hole theoretically a few years ago. Anyway, so what they have proved is that if you just assume the standard general relativity, then whatever happened during the course of evolution doesn't really matter. If you go back in time, eventually you encounter so-called singularity. Singularity is where the law of physics breaks down. So this means, you have a problem, because if you start from singularity, if the universe starts from singularity, you can't have anything. Singularity means that the law of physics is broke down, so which means that you can virtually have anything, or in other words, you don't have any predictable power. So this means general relativity should break down at a certain point before you hit the singularity. And that's where people think that you need quantum gravity. This is one, at least a strong reason for quantum gravity in cosmology. Now, what is quantum gravity? So quantum gravity is, by its name, you can easily see that the quantum theory of space-time, and this is not still well established at all. So this is just a kind of trying to look for something, trying to find some clues to the quantum theory of gravity by doing some experiment, theoretical experiment, let's say, and one of the way to do, for example, in cosmology, is to so-called quantum cosmology, and in this case, as I have said, the Einstein equation is very, very complicated, but as soon as you assume this large-scale homogeneous and isotropy, it becomes very simple, one equation called Friedmann equation. So similarly, maybe you can understand some quantum nature of, say, those quantum gravity by applying this quantum theory to homogeneous and isotropic universe. In this case, you just consider quantum mechanics of this cosmic scale factor. That makes things much easy. Now, and this would maybe give us some hints towards the full quantum theory of gravity. Anyway, a quantum theory, important thing is that in the difference, most important difference is that there is so-called quantum tunneling effect. In the classical theory, if the particle hits the barrier, it can be just reflected, and the particle cannot penetrate the barrier. But the quantum theory case, you have the spread of the wave function, which is described sort of a probability distribution of the particle, and the sum of the part of the probability distribution when it hits the wall permeate through the wall. Actually, so in some sense, your wave function would be divided in two, and nobody knows whether you're on this side or that side. But always there's a probability of some matter going through the barrier. This is the most important nature of quantum theory. Now, another thing is that there's this so-called a uncertainty principle, which tells you that if you go to some microscope scales, then this is the quantum fluctuation I was talking about actually during inflation, that there are always some fluctuations in matter, space-time, whatever. In this case, I'm just trying to think of this space-time fluctuations. So if you go to a very, very small scale, you have this so-called uncertainty principle that if you go to very, very small scale, it means that the length scale very small, then you have some uncertainty in energy which becomes larger and larger. Vice versa, if you make the very small energy limit, then the L must be very large. And there's this limit that in some sense E times L is greater than something, which is given by this Planck constant. Now, if you use this and apply to gravity, then you find that at scale, the length proportion is equal to about 10 to the minus 33 centimeters. You hit some characteristic scale where space-time becomes fully quantum, meaning that you cannot really define the whether space is space or space is time, and so on and so forth. There's no notion of space-time ceases, and that is called the Planck scale. And this was originally proposed by this John Wheeler. He named it as the space-time form. That if you go down to this small scale, then our universe would have been very, very chaotic from space-time sense. Not just the quantum fluctuation of the field, but it's a quantum fluctuation of space-time itself. Now, what would this imply in cosmology? And there was this very, very smart person, Alex Vilenkin, already like 50 years ago or so, realized that if we consider some universe which is actually has some zero, but if you have this vacuum energy dominated universe, then you have some effectively some barrier, and the classical universe cannot penetrate. So if you consider some classical universe, it sort of go back, become small and become large. So bounces back. You never reaches this nothing. But if you use quantum theory, then our universe might have started from nothing to something. So this idea was called creation from nothing, and there are many discussions going on still, and what kind of wave function we should sort of have, and how to compute, and whether it is consistent with observation, and so on and so forth. There are still lots of discussion going on, but essentially this is a very, very appealing theory, which sort of tells us maybe there were no universe, no space-time, but our universe was so spontaneously created. Of course, this is something it's not yet to sort of proved, because as I said, we don't have any quantum theory of gravity, so this is just a model, and we think it does contain some truth, but we don't know which part is really the case or which part is not. Anyway, so to summarize, it seems that maybe if this Vilenkin's idea is correct, we started from nothing and we become something. Hopefully we are do something, right? I mean, some people think we are nothing yet, but anyway. So then the baby universe, perhaps Planck-sized baby universe, it inflated to a huge, gigantic size, and this vacuum energy is turned into to heat, and it formed the Big Bang universe. So that's the current sort of status of the cosmology. Now, let me just briefly mention what might happen in the future. So there are various possibilities. No one knows what would happen, but unfortunately, none of them look so, happy or interesting. But anyway, so if the universe expands forever, maybe the expansion rate decreases, and they need indefinitely to sort of go towards kind of a static universe. In this case, what is waiting for us is so-called thermal death. Nothing happens. There's no thermal energy, and everybody is far spread apart, and we just silently die. Yes. Another is that the exponential increase indefinitely. This is called big cliff. This is again not so happy thing, because now universe expands so fast that even locally, within, for example, this size of a room, we feel the expansion rate of the universe. And eventually, this expansion rate becomes so huge that even our bodies sort of ripped apart. Everything is ripped apart. That's another very sad end of the universe. Another is expansion at the constant rate. So for some reason, we started to expand it at the constant expansion rate now. Maybe there are some, another sort of creation of some things due to some, I don't know, quantum fluctuations or some theory of some gravity and some thought. In this case, we have, say, eternal inflationary stage of the universe waiting for us. That may, in some cases, that may have some interesting sort of my lifestyle, form of life or something, and we don't know. So this is the only sort of case which might have some good future. Anyway, if the inflation, by the way, expansion stops, of course, the universe would contract, become and collapse to a point, and then that we call big crunch. If this big crunch means the end of the real space-time, or maybe there's new universe waiting for us in the next stage where, of course, we cannot go through. We don't know. Anyway, so at least I think we have to wait for another 10 gigayears or so to see which direction we are going. I say, please live long. Thank you. Oh, by the way, and I hope this is correct. Yeah? Okay, good. Thank you.
Thank you, Professor Sasaki, for his excellent talk and his lucid talk. And the greatness of this talk is that it covers all the topics we plan to discuss in the conference, so the students can have a broad overview of all the topics, and it's good for them to participate in the conference. Now we can move for a couple of questions. We have like 15 minutes on schedule if you have questions.
Thank you, Professor Sasaki, for your nice talk. Maybe my question will be naive. So you are explaining about this big crunch. So my question is, so what the vacuum energy you have, so when its expansion stop, so this vacuum energy, this pressure direction will be changed, or the negative to positive, or the dark energy will be destroyed, or means to say it will be converted to the gravitational collapse.
Well, thanks for the question, which I'm sorry I cannot answer. Yes, there is, as you pointed out, there are several possibilities. Yes, and the simplest is that yes, the vacuum energy, if we can prove that it's actually decreasing, and if this decrease is not sort of maybe not stopping, then you could go through zero and become negative. If the vacuum energy becomes negative, the universe, instead of exponential expand, actually it's sort of exponentially crashing. Yeah.
So I have a long time now to be in dark energy, right? So for research, no, it is not so. Okay, thank you.
May I speak in for the Thai participant? If you want to ask a question in Thai, I would be happy to translate. Anyway, Luis, your question first.
Thank you, Professor, for your nice talk. In your research experience, do you have any favorite model for inflation? Any inflationary model that probably could be confirmed in the next years?
Well, actually, I don't have any favorite models. I have some model which might be interesting because, interesting models should have some interesting predictions which can be proved in the near future, right? So, at least I try to think such models and see if there are interesting implications. But I'm open in that sense. I'm open to any models. And right now, there may be some sort of observationally favored models, but they are also only just small fraction of all the model space. So in that sense, I would just say I'm open, but if you have some interesting models which can predict something else, something, addition, that would be great. Yes.
Any other question?
Continuation of that question. We usually validate inflation model based on tensor to scalar ratio, right? So this is a growingly saying that scalar ratio to model is coming smaller and smaller. So my question is, no model is going to agree with the scalar ratio. So what will do the inflation models?
So again, please.
See, inflation models basically can validate based on the tensor to scalar ratio, right? Mm-hmm. So each model predicts its own value, tensor to scalar ratio. Now you can see that this value is coming smaller and smaller. Many models are not agreeing to that one. In future, no inflation models agree to that value. What will happen to the inflationary models?
Oh, okay. Yeah. Well, so the scale to tensor ratio people talk about is on this CMB scale, and definitely we hope that the ratio is large enough to be detected in the near future, but maybe we're unlucky to do so, huh? And in that case, at least from the CMB scale physics, we cannot prove, or we cannot say anything about inflation. But there are many sort of scenarios which can actually amplify those amplitude on small scales. So this is related to this direct detection of gravitational waves. And it does depend on what kind of, evolutionary behavior of universes and so on and so forth. Everything depends on some details. And of course, if you just give one assumption, one result, it doesn't mean anything. But if you have other predictions, and if the prediction can fit with such models, then that would be another good sort of a test of inflation models, I think. Is that okay? Yeah.
Yeah. Thank you very much for your nice presentation. So I was just asking that when we do the early inflationary scenario for large scale structure, etc., we take the quantum fluctuations, go to the super high valorizer. So we do the semi-classical analysis, right? So I'm asking that, in your personal opinion, how far we can push the semi-classical analysis, or in future could we test a little adventurous, like like quantum gravity itself? Like the B mode would certainly give the inflationary scenario, but whether the semi-classical analysis is correct or we need much more deeper than the Planck, then that. What is your opinion? That's just I wanted.
That's a very, very interesting question. Yes. So in this kind of what we call vanilla type inflation model, yes, everything happens in a fairly simple manner, and it's as you say that we think that all this semi-classical analysis would be justified, and also actually it's very, very difficult to see the real quantum effect, but. Of course, so there may be some other sort of scenarios or occasions where the initial state of universe was not exactly what we anticipated, and then in that case you might have some non-trivial correlations in the state, which gives rise to some quantum nature, which maybe we can prove or we can experiment in the future. And that's a hope. But of course, and there are several ideas, but at the moment, this is just a kind of, what do you call it? Theoretical, not even a conjecture, that's some modeling things, yes.
Yes, sir, that's it. No, I was just wondering because in black hole, we can do the semi-classical analysis and get the Hawking temperature. We can do the same calculation in loop quantum gravity and string theory, we get the same entropy, black hole entropy. So that's why in cosmology also, if we do the same thing, like the semi-classical one and the string one, it would be great. So that's why, thank you.
Maybe I misunderstood your question, but
No,
yeah,
it is fine.
Yeah, no. So yeah, well, so far we do treat everything same classically, right?
Yes.
And nothing looks wrong. So I don't know. I mean, I don't know how to answer your question.
No. That is fine. I am saying that in black hole, the semi-classical.
In the case of
result-
black hole as well, we think the semi-classical approximation is valid.
Yes.
But as you probably know, that in these days, they say some people say no. Even at the very, very sort of, for example, if you consider the one solar mass black hole,
Yes.
after the Hawking radiation, make the mass decrease to say half of the mass, then quantum gravity comes in, and that sounds very, very strange to me, but. Still, there are theories which tells you so, but so far we don't have any, way to prove or disprove such theories. Yeah.
Thank you very much, sir.
Yeah.
Any other question? Okay.
If I would speak Thai if you wouldn't mind พวกเราที่เป็นนักเรียนคนไทยสามารถถามได้ถามคำถามอะไรก็ได้เพราะว่า you're not a scientist you this is a public talk so you can ask anything ถามอะไรก็ได้ถามอะไรก็ได้มีไหมที่เด็กๆโอเคI will just try to translate
คือผมอยากรู้ว่า dark energy นี่มันคืออะไรนะคือเห็นอยู่ในสมการ
So it's a naive question. What is dark energy and why you put it in the equation? What is for?
Well, actually it's kind of a cheating. I mean, the dark energy means that we don't know what it is, and because we don't know what it is, we just call it dark energy. Yes, so it's a name without a name.
ท่านอาจารย์ก็บอกว่าที่เรียก dark energy เพราะเราไม่รู้ว่ามันคืออะไรก็เลยใส่ชื่อไว้อย่างนั้นแต่จริงๆมัน dark หรือเปล่านั้นจริงๆมันไม่น่าจะ dark เพราะว่า dark เพราะเราไม่รู้มันแปลว่ามืดเท่านั้นเองแต่ว่าไม่ให้ add something so ก็มันเป็นพลังงานที่ทำให้กระพบเนี่ยมันขยายตัวแบบเร่งคือเอกภพมันเร่งออกปัจจุบันนี้แต่เราไม่รู้ว่าอะไรทำมันเร่งออกเราก็เลยได้สารนั่นหนึ่งที่เรียกว่า dark energy ขึ้นมาแล้วก็ใส่เข้าไปมันก็เร่งออกแต่เราก็ยังไม่รู้ว่ามันคืออะไร because we don't know ไม่รู้ so we put dark but it's not dark okay thanks ขอบคุณมาก you so brave
There's some question over there.
Any other question?
So when you're talking about Big Bang, when you reverse the adiabatic expansion, right? But now if we have the vacuum energy, when you reverse it, you should lose the vacuum energy along the way, right? Is it possible that we don't have Big Bang at all?
Wait. When you say Big Bang means this hot Big Bang. As I said, we do have a ample of evidence for this hot Big Bang or hot and dense early universe. So as far as that point is concerned, I don't think there's any other models. And I think essentially, probably, I hope everybody doing science agree with that point. Beyond this hot Big Bang, we don't know. Yes. Yeah. Is it okay to answer your question? Yeah.
Any other question? A quick question because we are running out of time. So we have a couple of questions online from online participants, I think. In Planck, we don't see any primordial gravitational wave. Is it a result of our observational capacity?
Yes, we do hope so. I mean, in the beginning, actually, before we had sort of a better hope in some sense that the Planck could find this reminiscence of gravitational waves. Unfortunately, that was not the case. So we only have constraints on the amplitude. Yes, right. And if we never detect, then what? Yeah, this is I already explained. Maybe there are some other. I mean, the CMB is of course a very important experiment, and it's so one of the most important targets for gravitational wave cosmology, let's say. But there are many. I mean, it's essentially one very low frequency experiment. We can do some high frequency experiment which can detect those primordial gravitational waves.
จักรวาลคู่ขนานมีอยู่จริงไหมคะ
Okay. Now is the parallel universe exist?
It depends on what you mean by parallel. If you, for example, I mean, there are of course theory which I don't know. I mean, it's the multi-universe, or I forgot the name, but anyway. So every second, your universe is split into two. Every second, you are in the living other universe, and so on and so forth. Well, if you sort of apply this kind of wave function. One of the natural consequences, but we do think that this is probably too naive, and so we are not really splitting into different universes, but we don't really know how. Sorry. Yes.
โอเคก็อาจารย์บอกว่าก็ยังไม่มีใครรู้แล้วก็เป็นคำถามที่ยากแล้วก็เป็นคำถามที่ตรงๆมากๆเลยอาจารย์บอกว่ามันยังไม่มีวิธีการที่จะไปจักรวาลอื่นนะแล้วก็ถ้าเราใช้คอนเซปต์ของควอนตัมแมคานิกเนี่ยก็ต้องพูดถึงเรื่องการสปลิตเวฟฟังก์ชันเป็นเทคนิคนิดนึงแต่ว่ามันก็เป็นเรื่องน่าตื่นเต้นนะที่เด็กจะถามเนาะ It's exciting for kids to ask usually. You might encounter the question like, can we go back in time and so on? So from the high school kid, you know.
Well, I don't know. I mean, that's a really hard question. What we call this causality tells us, since we think that in the past of our existence, there was not really something strange happened. I mean, at least proved things. So this means that if there was some time machine discovered in the future or somewhere, and then those people, those creatures would perhaps come to present on the past of our history and affect our history, and but we don't see them. So from that point of view, probably it's not so easy. Right? Probably it's not possible even for these highly advanced sort of civilizations. But we don't know. I mean, okay, not from observation. Sorry, theoretical point of view, this is possible. Yeah, but it doesn't. It is inconsistent with causality, which we do believe. So we don't know.